Alright, ladies and gentlemen. Oh, should move my microphone. Alright. Ladies and gentlemen, class recording has begun. Yesterday, Mr. Roby played you a video. I knew you guys would miss me yesterday, so I decided to record a little video so you could at least hear my voice, you know, and
we all agree that Mr. Roby looks like the guy from Phineas and Ferb, the robot.
Norm?
Yeah! Oh my god. That was Norm. You just really
I could see that.
Oh my god. That's so funny. We were like, you look like Norm. He's like, thanks.
I could see that Mr. Roby
Totally.
bears a resemblance to Norm. I could see that.
Every time I see my
Alright. Good thing that we got that on recording.
Maybe
Mr. Roby's probably Vortex Lord.
Who is Vortex? What?
Anyway.
Macho makes a comment saying that.
Alright.
Wait, do you get like a lot of views per video? Just like. Are you like trending?
Are you in YouTube?
Are you like
Wait,
trending
is
topics?
Vortex?
Getting that YouTube money.
Do you have a droid?
Yes.
And do you have an Instagram? What an Instagram?
Oh my god,
I'll follow you.
Instagram!
I would totally follow you.
Alright. Yesterday.
That's unrecorded.
I know. Yesterday, you guys started on the sound stuff, and I hope that a lot of the stuff that we heard yesterday was review stuff. So first, sound waves are mechanical and longitudinal. What does that mean if we say that sound waves are mechanical and longitudinal?
Sound travels through a medium and
Okay, that's which part?
that's
mechanical.
That's the mechanical part. That sound must travel through some kind of a medium. Chris, go ahead.
The longitudinal part means that the wave is traveling with, or like the current or whatever.
With the wave.
Yeah,
Parallel, right? So instead of like going up or down, the air kind of like gets scrunched together and then spread out, and scrunched together and spread out, and scrunched together and spread out. Okay, that's the longitudinal or a compression wave. Yes. Okay. Right. So this picture, this is a demonstration, and if you want to see it, just pop it up on YouTube and put bell in jar. If we take a vacuum and get rid of all the air in this jar here, you won't be able to hear the bell anymore. Okay. It's the reason why astronauts can't just talk to each other, even if they yell really loud, right? If they don't have, you can't because there's no medium for it to travel through. So, then we talked about that sound travels at approximately 340 meters per second, which is about 765 miles per hour, give or take. Okay, so pretty fast. Anything good?
Wait, so if you're in space, can you hear yourself?
You can hear yourself inside your suit, yes, because inside your suit there's air. Okay, but as soon as you get outside of your suit, you can't hear anything else.
Well,
Unless like that's why they have to use like radios to talk to each other. They can't just like yell. Okay. Now you can hear the radio because there's air inside of your suit, so it had the sound has something to travel through. Okay.
Oh, but when
What if you were just sitting in space with no suit? Could you hear yourself?
No.
Like
You would
no
die
suit?
instantly.
Oh,
Right.
did you hear yourself? Yeah. I obviously other than the fact that you died, but you know.
How does it take for you to die?
Death is zero.
Parker, I'd probably say
How
yeah.
long would it take you to die under water?
Wait, what was
About
Like without any
no, faster than that. So.
No, but doesn't like your body just like kind of compress almost?
Well,
Like it kind of like.
like two things sort of happen. Okay.
Total
Recall.
First,
First thing. So, the pressure in space is obviously very, very low. Remember we talked about the idea that something boiling depends on both temperature and pressure. And we talked about the phase diagram, stuff like that, and that you can get things to boil at different temperatures at different pressures. Well, as the pressure goes down, the temperature at which stuff changes to a gas increases as well. So the pressure in space is so low that any water at that pressure would boil very quickly at a temperature that's your body's temperature. So if you just had water in your hand, it would start to boil because your temperature is hot enough for it to boil because the pressure is so low. Which means,
would you
but
boil?
yeah, that your blood is mostly made of water, and so it is, and that's the thing too, is that it's boiling, right? But then it's cold, so like you know.
Is it painful?
Probably pretty painful. Yeah, I mean you're dying after.
How do you think that? How long do you think?
About 15 seconds.
15 minutes.
No.
Whoa,
10,
what are you gonna
10
do?
15 seconds.
Well, you're not
Watch the
gonna
movie
break,
Total
so-
Recall, then you'll
Oh
see.
my god.
Yeah. That's why
see
that's
that
why
movie?
space is kind of a hard place to go to. Why we can't just like, you know,
Yeah, run a circle.
say, hey, you wanna go to space today? Like,
Oh
you know.
my god, I didn't even know.
I mean, it's like getting there is kind of hard. Once you're there is, you know.
Wow.
Can you just can you like go in space for like 2 seconds and come back down?
Yeah, for sure.
Getting there is kind of hard. I mean, there's no sign that says, hey, welcome to space. You know? Like what space is kind of.
Closed hours, Monday
Like,
through
is there
Friday.
Is there like a plane that can
Yeah,
take
that's
you there?
They're
No.
developing.
When
You know,
there's
it's
planes,
like-
there's planes that can go high enough where like the pressure is low enough that you have to wear a spacesuit basically.
But like, could
Didn't
you
that
see,
guy
like,
Put the.
Didn't that guy do that
Yeah.
thing in the hot air balloon or
Not yet. So this summer they're talking about it. So
What, a hot air balloon to space?
Who would that?
He float away into space.
we've talked about that guy.
Yeah, we watched this movie.
Yeah, we watched this movie.
Oh, that's the same guy.
So,
And like he got a
what?
hole in his
Same guy.
suit.
Yeah.
In his hand, like started expanding.
Yeah.
Yeah.
Very good.
Okay, so didn't that guy get like a rip in his suit?
Yeah.
Why did he die?
Because he wasn't quite in space necessarily. So the pressure there, he was still within the atmosphere, even though it was pretty low, and like there was a little hole there, but like there's other spots that they kind of like have like there's like barriers, yeah, like so that if something happens like that, you know, like in a spaceship, if one part gets a crack in it, they have to have some way to sort of section that part off, because if not, they're screwed. You know, like if there's one little crack, then you know. So they gotta kind of like on a ship, you know, like you know how a ship is built, like not a spaceship, but like an ocean ship. So, like there's like bulkheads in it, and they have like
Like the Titanic, like when they like build up.
exactly, yeah. Like they're the way that they build ships. I don't know if they still do it or not, but they kind of like build it in sections. And so if one part gets a little crack in it, they can sort of like they can like seal that section off so the water doesn't fill the entire ship up.
The Titanic.
Yeah, except
Except that we're
because there were too many sections
like
that
the
were.
scene where like they burst into the iceberg and then they're all like close the doors.
Yeah.
The guy got cut in half. That was weird.
Guy got cut in half. Yeah. So I don't know if that actually happened or not, but you know, or if that was
All
just
the
dramatic. but-
Titanic survivors died.
The last one-
Yeah, the last one
one
just
died,
like passed
like,
away
a
like a couple.
year.
I thought it was like this year.
No, yeah, like it was on Yahoo a couple months.
Yeah, I thought it was like
Yeah,
this
yeah,
year. Yeah.
But the actual girl, didn't she die like 2000 something?
Who?
Rose.
Like Rose.
Was that an actual story?
She was not
Yeah, they're not
That
real.
was a story.
No, that was like a legit story.
Oh my god, Alice.
But I could
She
jack
lost someone.
Okay.
Was the guy just
Oh.
started Leonardo DiCaprio?
Alright, so, you know, like, if you get like a hole in your suit, and it blocks it off so you don't get space, wouldn't that like, let's say you get a hole like in your arm, wouldn't that start boiling?
Yeah, and that's why like his hand started expanding, but it ran into his glove, so it didn't like pop like a balloon, you know.
But you'd be hurting a lot.
Probably, yeah.
I'm right.
So, has there ever been a reported case where somebody commits suicide over
Not that I know of.
Yeah.
But it's suicide to go to space.
Suicide by what?
No, it's still the same.
Alright, so
What's the best way to commit
Or they
suicide?
shoot themselves all the time.
Oh my god, don't break.
Stop talking.
Good job.
So, also, sound is going to travel faster when the temperature of the medium increases because those particles move a lot faster, so they run into each other a lot more often. Then yesterday, we went over two words that we've used in class before. The first one was intensity or volume, and we said that that's pretty much related to what about the wave? And that's what what measure of the wave tells us that? The amplitude of the wave is related to its volume. Not entirely. There's some other factors that go into it, but the amplitude of the wave definitely influences its volume when we're talking about sound. And then the other one,
So like how fast the energy,
what did we say amplitude was?
how tall.
How tall it is.
No, but I'm saying like the rate at which the energy flows.
So, it's the
It's like a
intensity
measurement over-
is the rate at which energy flows. So you have to talk about how much energy there is and then how fast you get that energy.
Yeah.
Right? So the amplitude tells you how much energy there is, and then how far away you are from the sound and stuff like that. That will tell you how fast it gets to your ear.
Oh, like the intensity of it?
Right. So
So
but
it's a
volume is related to the amplitude of the wave, although not exclusively. Okay. That's one thing I want you to kind of remember. Okay. And then the other term that I told you guys about yesterday was pitch, and the pitch of the sound is related to the frequency of the wave. That higher frequency waves result in higher pitches, lower frequency waves, lower pitches. Go ahead, Tim.
This says intensity depends on the wave's amplitude and distance from the sound source.
Yes.
Why?
Okay, so intensity is basically how much energy is reaching you. Okay? So we said that, Sam, the amplitude tells you what about a mechanical wave? What does the amplitude tell you about a mechanical wave?
From like the started, like
That's how tall it is, right? But what does the amplitude tell you about the wave? What does it represent in a wave? You want some help?
Yeah.
What does the amplitude tell us about a wave?
How much energy?
How much energy it carries, okay? So, or how much work was done at the beginning, okay? But Sam, as that wave travels outward, right, what do we know happens to the amplitude of the wave? It decreases because there's less energy because it runs into like friction and stuff like that, right? So the farther you are away from the source, the less energy is reaching your ear because it keeps getting turned into heat and stuff like that. Okay? We get that? All right. So the next slide I'm going to show you is in yellow, which means it doesn't really show up on your outline anywhere, but it's, you know, things that are important, or at least that you should be kind of familiar with. So your ear. How do we turn these sound waves into what we refer to as sound? Good.
The bones vibrate.
Okay. So first thing we got to do, okay? Outer ear. This part that we see.
Is there anything we write this down?
Oh my goodness.
Wow.
Just saying. You need to pay attention.
Yeah.
It's in yellow.
So
Yeah, even
your outer ear. That's the part that you see. Okay. Basically, your outer ear is just a big funnel. Okay. But it's a big funnel. Okay. We said that the volume of something or the intensity of that sound relates to how much energy gets to your eardrum. So what is your ear? What does this part of your ear do?
nothing.
Well, I mean, it just
It
catches
looks pretty when you have a cartilage.
There you go. So, it just funnels stuff down into your ear so that more energy is getting there, right? It's the same thing as if you do this if you can't hear something, right? Okay? Now you're just making that funnel a little bit bigger. Or if you've got like a big megaphone, instead of using it that way, if you like, you know, use it this way, you put it against your ear, all you're doing is just funneling more energy down into that ear. And that's what the outside of your ear does, basically. Okay? Your outer ear basically ends with your eardrum. Okay? That energy that you receive is energy. And we said, what does energy do? What is energy?
Ability to move.
The ability to move stuff, the ability to do stuff, the ability to change stuff. And the things that it changes, or the thing that it changes, is your eardrum, and your eardrum vibrates. In the middle of your ear, just past your eardrum, there are 3 tiny bones. Okay? The hammer, the anvil, and the stirrup. No, you can't see them. They're past your eardrum. Okay?
Can we touch our eardrum? Yeah, where's our
Yeah,
the
if
eardrum?
you ever like stuck a tube in your ear
Yeah,
a,
it
a little too far,
Yeah.
you know, and
It
it
makes
hurts.
me like
It
gag.
hurts so
Oh, I
bad.
have a story. One time I put it in my ear, like too far, and it bled out of blood.
Yeah.
What?
Yeah.
Not cool.
That was a while ago.
Oh my
But-
god.
So,
I don't know why.
yeah, that's pretty much when you push
Yeah,
the
it
Q-tip in
hurts.
too far, yeah, they're like that. So, anyway, past that, okay, there are 3 little bones. How little? Well, they fit inside of your ear. Okay, so they're the 3 smallest bones in your body. Okay, the hammer, because one looks like a hammer, and then one looks like an anvil, which is you ever watch
There's
like
an ear
you ever,
drum and an ear hammer. There's so much.
do you ever like watch Tom and Jerry? You know that like big metal thing that or like Wile E. Coyote, that big like metal thing that falls
what
on top of Wile E.
blacksmiths
Coyote. That's an anvil. You know what is it used for? I don't really know. Okay.
It's the blacksmiths use it to pound things.
Yeah. So okay. Here's your good.
So wait, does your ear end like where it connects to your head right
goes further into your ear. It goes further into your
So it's
head, right? Yeah, that if you look at a skull, you'll see that there's like a hole there, and that's where your ear comes in. Okay. So,
No.
yes, Miriam.
So like, I know this is a dumb question, but we can't touch our brain.
I mean, not without
rip
like
through
ripping through
everything.
stuff. Yeah. So
Oh.
yeah, there's no direct passage to your brain. So.
There's
What about
Can you get to your brain
deaf
through your nose?
people?
You can't get to your brain through your nose, but you have to like go through something to get there. So.
Oh, gee. What about deaf people? What are there like different things wrong with that?
Yeah.
Or is it like usually?
So then let's finish this up. So after the little bony part there, inside of your ear, okay, there's a bunch of like little hairs inside of there, and they vibrate, and that causes nerves to send messages to your brain, and then your brain interprets those vibrations as sound. If your ear tells your brain that it's feeling a vibration of a certain hertz, your brain interprets that as a certain sound, or whatever that may be. Okay? So basically, the outside of your ear gathers all the energy, funnels it down, your eardrum vibrates, it causes the bone to vibrate, it causes the hairs to vibrate, and then they send a little message to your brain and say, this is the vibration we're picking up, and then your brain goes, oh, that's such and such. Okay? Miriam, go ahead.
So it's like it travels at the speed of sound. Does that mean everything I was hearing you say comes after you've actually said it?
Technically, yeah, although like a couple slides ago we said sound travels at about 765 miles per hour, so it doesn't take sound that long to get from here to your ear, right? But technically, yeah, there is somewhat of a delay. Now, I mean, if you talk about like you're far away, right? Somebody can like yell, and it might take a fraction of a second for you to hear it, but yeah, it depends on how far you are.
What about, is it like for like math or something? Would it be a little bit more of a delay than
Technically,
like
yeah. Although how
I mean, not
yeah, right. If it's going 765 miles per hour,
I know,
that's
but
not
there
much of a
is
difference. But
technically
yeah, okay. Alex, good.
So wait, does that mean every sound we hear is like different for each person?
Yes, that we'll get into that a little when we get into pitch. Okay. One of the last thing that it wrote on pitch is.
Pitch depends on several factors.
Right.
How
Pitch depends on several factors. So how you hear me, Alex, might not be exactly the same as how Naranj hears me. And that's not to say that it's not my voice, it is, but hearing something is not just a matter of picking up a vibration, it's also a matter of interpreting that vibration. So that's why we're all a little bit different. Okay? So Sam, back to your question, people who are deaf, there could be a couple things wrong.
Right.
Okay.
Yeah, but like,
If you're deaf, like from an early age, like if you're born deaf, usually there's something wrong in the inner ear part, like that your brain doesn't get the message from your ear. Generally, if you're deaf from when you're born, that's usually the problem. Okay. But if you go deaf because of a traumatic experience or a loud noise, or if you may see like if you may. If you get stabbed in the ear, or
Yeah.
you can hear about like soldiers sometimes who are deaf because of an explosion, right?
Yeah.
Because generally that's an outer ear thing. Like they've received so much energy that they ruptured their eardrum to the point that it can't really be repaired anymore. And if that's the case, then sometimes if you have a really bad ear infection, you can get a ruptured eardrum, but it's skin. It will grow back. Although, Alex, that might be that you might not hear things the same way anymore.
Yeah,
Because
no, that's what happened to me a couple of years ago.
so your eardrum might have like a scar on it because of the fact that it rips and then it had to repair itself, just like you get a scar on your arm or your leg or whatever it is from a cut.
So can you break those bones?
Technically, but technically you could break them, but yeah, they're so small that. Lauren, go ahead.
Okay, so how do we know that
Technically, yeah, I would say it's hard to do, although you could kind of, I don't know what the research has been done. I suppose you could look at like electrical signals in the brain and see if different parts of the brain are lighting up, or you could maybe hide behind the fact of, well, everybody's different a little bit, and so from that standpoint, although I don't really know the research.
I think you could never know. Because
Right, because how could you, this gets into some color things too. Like, well, what color is this? Well, it's yellow. Well, what does that mean?
That's green.
So, okay. But no, the thing being though, Grace, if your whole life somebody told you this was green, you would look at it and go, well, that's green, right? But how do I know that, like, are you seeing it the same way? Or, I don't know, I mean, does that make sense?
Yeah.
I know you were trying to be funny. Trying,
Yeah.
being the operative word there. Because I know you weren't funny, so you must have been trying to be funny.
Thanks, Bagger.
So anyway,
So wait,
Kirsten, go ahead.
like when colorblind people say like a colorblind person would think that was purple, but they don't know if they're actually seeing it as purple.
Technically, yeah. Now there are some tests for colorblindness that you can do that they can't actually see certain things because they can't distinguish between the colors. If you've ever seen it, like a lot of times in books they'll do it, like there's certain colored dots that like make a pattern, like there'll be a circle, you know, and some people can't see the picture or the letter because they can't distinguish between one dot and the other dot. So, you know, from there you can say, okay, well they're definitely not seeing that difference. Yeah. All right. Next, ultrasound, which is not yellow, so it does show up on your outline. Yeah. It's somewhat yellow. Kind of ish. That's more actually green. At least I think
It's
it
a
is.
line.
So,
That's yellow green.
ultrasound. Your ears, or actually more your brain will interpret vibrations that generally range between 20 hertz and 20,000 hertz. So I don't think I did this demonstration for you guys in class, but here, let's do this. So, we refer to things higher than 20,000 hertz as ultrasound because they are, quote, above sound. Okay?
Wait, ultrasound like a baby ultrasound?
Yeah.
I did ultrasound.
So, let's go in the other direction. Okay? Here, ready? So, am I creating a disturbance in the air?
Yes, I can hear.
And disturbance to the
So,
power.
generally, if we talk about, okay, this is like 1 second, right? Okay, 1,000, 1,002, 1,003, 1,004. How many cycles am I making every second?
1%.
One per second. So my frequency of this disturbance is what? 1 hertz. Okay. Is this disturbance making waves in the air in this room?
Yes.
Yeah. What's the frequency of those waves? 1 hertz. Okay.
I did it 20 times over here.
If are those waves getting to your ear?
Yeah.
Yeah.
Yeah, but we can't
But I can't do it.
But they're hitting your eardrum at 1 hertz, 1 per second. Your brain or your ear interprets that in vibration and sends a message and goes, hey, vibration of 1 hertz. And your brain goes, so?
Yeah, awesome.
Yeah, like it's like,
Cool.
you know, it would be like, yeah, it's like speaking Spanish. It's like, or well, maybe not speaking Spanish because some people would understand that, but like, you know, it's your ear is sending a message to your brain that says, hey, I'm getting a vibration, and your brain goes, I don't understand that vibration, so let's just ignore it. So,
So
but
if
that-
I go like this, like it goes to like someone's ear.
Yeah. Anything go ahead. Oh, sorry, Parker, go ahead.
Is that why if you like spin a rope around really fast?
Yeah, right. That there is a disturbance here, right?
Oh my god.
There's a disturbance there that creates a vibration that's that's more than 20 hertz. Okay? And so your brain interprets that sound. Okay? Anything go ahead.
For like mosquitoes, how come like some people can hear it, but like
That gets into the idea that what frequencies your brain interprets as sound is not the same for every person. Generally, those tones are like lower pitched tones, okay? And they're like kind of at that borderline of can you hear it or can you not hear it. You can do the same thing on the upper end too, like can you hear it, can you not hear it. That's just a difference individually per person, okay? A lot of times the thing with like the mosquito ringtone or whatever is they sort of rely on that as people's ears get older, they are less sensitive to certain vibrations because it's like their eardrum is getting worn out. It's been used so much that it's getting worn out.
Oh, and is that why like my grandpa can't hear that well?
Right. Or what? Tim, do you like the mosquito ringtone?
Yeah,
right?
the one that
Yeah.
like
So from that standpoint, they're kind of putting it on the edge of, okay, if your ear isn't worn out, you probably should be able to hear this sound, but if it's kind of a little bit older and been damaged or whatever, you probably shouldn't be able to hear it, and that's kind of what they're banking on. But that really depends on,
Can you hear this?
I can hear
I
it.
can't even
I'm
hear
kind of
that.
far away, so.
I mean,
I can hear
I
it.
used to be able to hear it.
wait, ready?
I can.
Wait,
I can't.
it's not going anywhere.
You can't hear it?
I could only hear for the first. Yeah. I
There's
could
nothing
hear it.
playing.
Is it-
This is
it's going everywhere.
I heard it.
He can.
I used to be able to do it.
I hear it.
You're getting no, I hear the birds outside.
Wait, I was like,
At least you hear the birds. There's nothing else. You hear the birds.
Again.
No,
Yeah, but
well,
we're long.
I feel like it's still playing.
so yes, Alex.
So when you like whack the stick, you can do that with like a tennis racket or like anything, and you go fast. Why does it make that sound? Because it's faster than.
Yeah,
the
it's creating a
wind.
disturbance. It's creating disturbance in the air.
Oh, it's a
More
It's like then faster
Right.
than this.
Yeah.
You know what?
So,
When I was little, I used to
with ultrasound,
Let's see if I can
people
do that
lost
with
their
my
hearing,
hand.
it would be more like they were just so
Now.
sounds in the corner.
when we use quote unquote ultrasound, okay, couple of different applications. A lot of people think of the medical application, which is fine, and that's kind of where we do use it quite a bit, but it's not the only place that we use it. Okay? All it is a vibration. It's a wave, and we know that when those waves go out into a medium, if they encounter something hard, something solid, something that's different, there'll either be a change in the speed or there'll be a complete reflection. Okay? And if you gather up those reflections and go, okay, I see this one coming from here, that must mean it came from this point, then you can tell what's in the way, or you can tell if something's in the way or what shape it is. Sonar. Probably heard of sonar before. Yeah, like
Yes.
submarines and stuff like that. Okay, they're sending out sound waves. Dolphins, whales, things
Bats.
like that. Bats, same idea. Okay? They're sending out sound waves, and those sound waves go and they bounce off of something. And how long it takes them to get there, and how long it takes them to get back, and what frequency they're coming back at versus what they went out at. They can tell. Okay, is something coming towards us? Is something moving away from us? Is something sitting still? Is there nothing in front of us? That kind of stuff.
So is that only through water?
No, because it can go through any medium, right? Although it's generally easier through water. It travels faster through water than it does through air, right? The thing being that if you take it at a level of higher than sound, right? If you're in a submarine and you're looking for another submarine and you're sending out sound waves that people can hear, they know you're looking for them. You know what I'm saying? But if you're sending out sound waves that people can't hear, but they're bouncing off of the hull or whatever it is, the ship, now you can kind of find out where they are, but without actually the idea being them not knowing that you're looking for them.
So like we give off ultrasound waves?
No, generally most of the sounds we make are in the range of human hearing. Well, like a dog whistle, right? A dog whistle creates a sound that's ultrasound. It's above 20,000 hertz. But dogs' ears are sensitive to those frequencies, so dogs hear it, but you don't.
Oh.
And I'm not really sure what the range of dolphin hearing is. I don't know.
So we don't make that. We're like.
Yeah, a dog whistle is a whistle. You have to,
Okay.
All right, so we good there? Last thing on your outline, Doppler effect. We've talked about the Doppler effect like so many times now, but real quick, So Doppler effect, right? Change in the frequency caused by the motion of a sound source or a motion of the listener or both. As those objects are getting closer together, the frequency increases. As those waves get, or as the distance gets farther apart, the frequency decreases. Not going yet.
should go see if the Doppler effect happens at Cedar Point. Which it does.
Did I show you guys my Doppler effect demonstration?
No.
For real?
Yeah.
With the tuning fork?
No, you didn't. You didn't show us
What
anything.
tuning for? What's it tuning for?
Is that for a guitar?
Guys, this morning I woke up at 4:45.
Couldn't go back to
Because
sleep.
my grandma and grandpa, remember they have to go downstairs, they turn on all the lights in the house. So, and I only sleep with my door open, so I wake up with this like bright light, and I'm like, oh.
Why were they up at 4:45?
Because they have to go to Texas, they have to leave early.
Why would you have your door open?
Because I always leave my door open.
Excuse me.
So then I wake up, and I'm like, oh.
I see my
But
clothes.
sometimes they can hear stuff and people are still up.
So I was like, oh.
I know, I close mine and walk.
So I come out and
I close mine in case like I keep my open.
and I finally closed my door.
Fairly.
Then my dog came like nudging.
Safe enough that I can.
You can close the door after him.
You didn't go back to sleep.
No, like, up and down.
Alright, stand by for Doppler effect demonstration.
That's what that thing is.
That's awesome.
Oh yeah.
I've seen one
Doesn't
of
that
them
go
before.
like vibrate like?
So, this is a tuning fork, okay, in case you've never seen it before. And when you strike it, it vibrates at a certain frequency. This one is 440 hertz, which is an A. We figured out. Yeah. So, if you strike it, it sounds like this.
It's beautiful.
Okay? And if you strike it more times, right, amplitude increases, it's shaking back more and more, and so it gets a little louder. Okay? But as far as the Doppler effect goes, I'm going to do this.
Why don't you change the frequency of it?
So, as it's sitting here, okay, as it's just sitting here, you guys don't experience any change in the frequency because the distance between you and the tuning fork is exactly the same. Now, Chris is farther away from it than Alex is, but the distance between the tuning fork and Alex is staying the same, and the distance between the tuning fork and Chris is staying the same, so you guys both hear it the same way, within the limitations of human hearing and all that kind of stuff, okay? Right? But, if I change the distance between you and the tuning fork, like this.
Watch out for the shower.
Thanks.
Oh, that's cool.
Did you guys hear it?
Yeah.
So, this one doesn't ring for very long, so it's kind of hard for me to get it started and then get it swinging fast.
This reminds me of the Big Bang Theory when
Yes.
when they were like trying to figure out what his costume is, and it's like, I'll give you a hint.
What?
That was a good episode. Oh, it's,
What? A what one?
Big Bang Theory. It's like Halloween party, and it's just like, well, are you a zebra? And it's like, I'll give you a hint.
Penny was having a Halloween party, and Sheldon dressed up like a Doppler effect. And he had he just had a striped suit, and like the waves were like closer together on one side than the other side. So, and see, now when you guys go and watch that episode, you'll be like, all right, let's see if we can get this done quicker. Nope.
Nope.
That didn't work. Why didn't you
Hang it
just
up.
the first one
Hang it
work
up harder,
better?
so
The hitting one worked the
How about
best.
this? We should play. Someone hits it.
Hurry. You're taking too long.
Here it
I
comes.
learned it.
Hold on. Alright, ready?
Just start swinging.
Shut up.
I know what's fun. There we go.
Yeah.
What is this supposed to do? I didn't hear
I've
it.
heard it like the first
It
few
goes.
times.
Can you hear the difference
Yeah,
when
I
it's
hear it.
It's like,
Oh, yeah, yeah,
I'm moving up and down.
Can you hear it like get higher pitched and
Just
more
watch
good?
the Big Bang for the rest of the year.
yeah, the Big
Anyway.
Bang Theory is so educational.
So,
We should have learned about it.
Doppler effect.
We were learning
Here we go.
about some
Okay. Quick. Couple of things that are relevant to many of you. Okay? From a music production standpoint, okay? It's not the sound of music, it's sound and music. Okay. So, this one actually should be yellow because it's not anywhere on your outline. But anyway, so musical instruments. Musical instruments create waves of different frequency by changing the length of standing waves. Okay? Remember we went over standing waves last week?
We didn't.
Oh, you guys didn't get to the end of it. Oh my
Oh
goodness.
yeah, I was hoping that wasn't.
Yeah, you told us to watch it at home.
I know.
It's actually really good.
last week that if I create this disturbance in the spring, right, it goes down, it bounces off hand, comes back this way, blah, blah, blah. If I make a disturbance and then a second disturbance, right, they can pass right through each other, and the whole interference idea, right, constructive interference, destructive interference, blah, blah. Okay? If I create waves at a certain frequency, they will interfere with each other in a way that certain places in the medium will show constructive interference, where the amplitudes of the waves gets bigger, and certain places, certain points in the medium will show destructive interference, where the amplitude is smaller. Okay, you ready? All right, here we go. Okay.
I hear it.
Double dutch.
Okay, this kind of double dutch. Grace, that point in the spring that's like right in front of you. Actually, a little bit more than that, like right there. Okay. What's that point in the spring doing?
It's going up and
Is it do now? That's the
It's not
part.
really part of the weight.
It's not really part of the wave, right? Is that part of the medium moving?
yeah.
No. There's a part right in front of Grace there that's basically just sitting still, right? Okay.
But it's just hard to
So
see.
that now Sam, like you said, the parts around it are going up and down, but there's definitely a part in there where it's not moving. You're right there. Grace. Good. Okay. So that we refer to as a node. Are waves passing through that section?
No.
Yes. But they are experiencing destructive interference, where the one wave is on one side of equilibrium and then the other wave is on the other side of equilibrium. Does that sound familiar?
Sure.
Yeah, okay. But if you look at the other parts, the parts that aren't right in front of Grace, right? Here, and then in between the node and the other part, how far am I shaking my hand? Not very far. But how far is the spring moving each time? Yeah, a lot farther than I'm shaking my hand, right? So in that part, we are having constructive interference, where crests and crests are meeting up, or troughs and troughs are meeting up, so we get a bigger amplitude in those cases. Here, are there waves traveling down, bouncing off Lancashire's hand and coming back towards me?
Yeah.
There are. But they interfere in a way that it looks like this wave is just sort of standing still. We refer to this as a standing wave. Okay? So, how many standing waves was I creating right there?
Two.
Like
One and a half.
One.
One.
Okay.
yeah, because it has to go.
Okay. Up, down. Okay. Now, the up and down keeps changing. The up and down keeps changing as far as which one's up and which one's down. It's only one wave.
So this right here is like going up and then down.
That's like a half a
that's
wave.
half.
That would only be half of a wave.
Why
How
do
do
you
you
do
make
two
two
Because
waves?
this one's
Because
down and that one's up.
It's got to go. When this one's up, that one's down.
Yeah, I get that.
Well,
Okay?
try and
And
make.
that's a wave.
Isn't that two then?
Oh.
Because a whole wave has to go up and down.
What if they were both going up at the same time?
They're not. One's
Can you
up
make
and
two
one's
waves?
down.
No, up, down, up, down, up, down.
Now, when this one goes down, though, that one goes up.
So,
That's only one wave.
but like if you only had this one way, this.
That's only
like,
half of a wave.
Why?
Because it only goes either down or up. It can't be both at the same time.
Oh, it has to be both at the same
And for a whole wave, you got to have an up and a down. Okay? So, Sam, if we change the frequency, stop it. If we change the frequency, I can create another standing wave, or actually more standing waves. Alright? So let's do this one.
Wow.
No, is this like
So
one
is
and a
that
half?
one?
Yeah,
This
it's
is
one
one
and
and a half. Okay? Because there's an up and down and
Oh,
up, or a
that
down and up and
Not
a
do it
down.
You're so close.
Do it faster.
I throw something at it.
Make two waves.
Just so you know, okay, I know this takes away from, but this takes away from the standing wave sometimes, but if I don't say it, then sometimes I make a funny face when I'm shaking the spring this fast, so just, so anyway. So let's see if we go two, and none of you are gonna watch the spring now, you're gonna watch it. Alright, ready? Here we go. So,
Did you get a picture?
so,
Wow.
I know,
It's just like.
so, wait, can we see the two waves?
Yeah.
Wait, how many waves? Oh yeah, two.
Okay.
Ah.
You got, make sure you got one more in you.
Yeah.
Let's see if we can do 2.5. This one gets pretty tricky.
Oh my god.
Is this gonna be 4 of the like lumps?
That was 4 that
So
time.
this is gonna be
Now I was
5.
trying to make
That was
five.
4? Was that 2?
No,
well,
it
it's
was
2 waves,
4
right?
lumps.
But it's an up and down and up and a down.
No, I meant 2 waves. That's what I meant. What are those lumps called?
That would be like half of a wave. Actually, as far as standing waves go, we refer to them as antinodes. Okay, that's what they're
Oh,
called.
because you're not moving.
They are moving.
I know, that's what I
Nodes.
meant. That's what I meant. I'm
Yeah,
sorry.
nodes
They
are the
are
ones that
moving.
aren't moving.
That's what I meant.
All right, here we go. See if we can do 5. 2.5 waves. All right.
Wait, 1, 2, 2.5.
But
Go faster.
you can definitely see though. This one actually. Oh, I lost it. Actually, no, wait. So something to keep in mind while we're doing this, okay? If you watch the spring, there are definitely parts that you can see that aren't moving, and they look like dark spots because the rest of the spring is moving so fast.
So where's the node?
But the nodes are the spots that aren't moving.
Can you point, like...
Well, that's what I'm going to point out to you. Look at the spring, okay? And you should be able to see that there are like dark spots in the spring that aren't moving because their destructive interference is occurring at that point in time, okay? All right, let's see if I can do this again.
Oh yeah, like in the middle. Like in
That's
in
only
the, like,
2, but can you see that Alex, there's one like kind of like right in front of you.
Yeah, like right there. I see that
Can
one.
see.
Yeah, can you see like
Yeah, I
those dark
see
spots?
one and then one next in front of Chris.
Yeah, there's one in front of
Is it-
Chris.
there's not
There's
really-
one like right in front of Naranj, like right next, like right, a little bit to your right there, Naranj. Yeah, like right there where Grace is pointing. Alex, there's one kind of in front of you right there.
I don't really see this one.
What happens if you touch it?
Actually, it should be nothing, but you know. But you have to make sure that you touch that part, because if you touch any parts above or below it,
Oh wait, so if I actually touched this one little spot, it wouldn't do anything.
nothing should happen.
Oh my god.
All right. So those are standing waves.
I just ate a water balloon with my gum.
So standing waves.
That is so gross.
All right. Musical instruments work along the premise of changing the length of a standing wave. If you change the length of a standing wave, you change its frequency. Okay? Glad we got that taken care of. So, real obvious example. Okay? How do you change the notes that you play on a guitar?
Tighten the string.
Well, you can tighten the
Or you
string,
shorten the
or
you go like,
you change your fingers, right? Okay. By changing your fingers, okay, you change the length of the standing wave, and that causes it to vibrate at a different frequency, and that causes a different sound. Now, this other idea of resonance, if you make something vibrate,
It kind of sounds like Renaissance.
No. In English class.
smells like baking
something.
resonance, sound waves cause other items to vibrate, which greatly increases the amplitude of the waves produced, which increases the volume. Like,
Come on. Okay. Oh, it's not what I wanted. I wanted this one.
okay? So, like on a guitar, right? Could be a banjo. I think it's a guitar. Okay. So here, the guitar consists of this the big part down at the bottom, not just the strings. When the strings vibrate, they also cause the body of the guitar to vibrate. If you've got a bigger area vibrating, how much work are you doing on the air? More work. And so what does that do to the sound? Louder sound. Okay? Here, how have we done this before? You have the empty bottle, right? You go across the top of it. Right? How do you change the notes?
By drinking more.
By changing what?
The volume.
The volume of the water inside. Because that changes the length of the waves that are inside of the bottle. The waves go from the top of the bottle to wherever the level of the water is. So by increasing or decreasing the level of the water, you can change the waves. A big pipe organ. Big pipe organs have a bunch of different pipes of different lengths because they produce different waves, different wavelengths, and different frequencies. how's that as far as sound goes?
Why is there a harp?
Okay.
Is that a
A
harp?
harp, actually that's a piano, right? It's like piano, like top view. But a harp is the same thing. I mean, a harp just has a bunch of different strings that are different lengths, and depending on which one you